welcome to my session, C++23, What's in it for you? First, a little bit about myself. I'm a software project manager for Nikon. I'm based in Belgium. And I'm the author of a couple of books, and the latest one is Professional C++ 5th edition, which includes the C++20 standard. The 6th edition is being worked on as we speak. I'm also the founder of the Belgian C++ users group, and we try to organize like 3 to 4 events each year. But due to the whole COVID pandemic, this was a bit on hold, so I hope to restart this soon. All right, let's get started. So in this session, I'll be giving an overview of everything that's coming with the C++23 standard. So this includes all core language features and all new standard library features. The C++23 standard will be quite a bit smaller in scope compared to C++20, but still, as you can see on this slide, lots of interesting things are coming. This slide lists all the topics that I'll be touching on today, but obviously I cannot go into details on all of these features within the scope of a 1-hour session, but that's not the goal of this presentation. So the goal is to give you a high-level overview of all the things that are coming, and there will be references to the presentations on CppCon this week if you want more information about a certain topic. So I have quite a bit of material to go through, so I would like you to ask your questions at the end of the session if time permits. You can use the slide number in the lower right corner as a reference when you ask your question. All right, let's start with the new C++23 core language features. First one I want to discuss is deducing this. So when you write a class, you will often have different overloads for const and non-const members, and possibly they are even ref qualified. So in this example that you see on the slide, I have a person class which basically has a single string data member. And then we have 4 overloads for a function called getName, and they are ref qualified. So we have 2 for const and non-const L values, and we have 2 for const and non-const R values. So why do we want this R value overloads in this class? Well, it's to optimize performance. So the getName basically returns the name of this person, and if we are working with a temporary object, we might as well just move out the name to the caller so the caller can reuse that memory. So in the lower right corner, you see one of these references to another presentation here at CppCon this week. So of course, having these 4 overloads, it means there is quite a bit of code duplication, and you can avoid that by delegating everything to a helper method, but this can become cumbersome in some situations. So how can we use deducing this to remedy this problem? So we can just remove all 4 of these overloads and replace them with this single function template. So getName now becomes a function template. The return type becomes autorefref, and the first parameter is this self refref self, and that's the deducing this feature. Now, inside the getName, you should not use this any longer. You should use self. So in this case, I'm just forwarding to self.myname. Deducing this also allows you to write the ref qualified numbers differently. So up to now, you always write ref qualifications by adding 1 or 2 ampersands at the end of your signature. So in this case, F can be called only on L values, G only on const L values, and H only on R values. But these are very short names, and these functions don't have any parameters. So if you have more meaningful names with a couple of parameters, these ref qualifiers can easily be missed, for example, during a code review. With deducing this, you don't use the ampersands at the end of the line or the signature, but instead you specify them like as follows, and in this case, it's harder to miss these things during a code review. And finally, deducing this also allows you to write recursive lambda expressions. So normally, when you access this inside the body of a lambda expression, it will access the object that contains your lambda expression. It will not access the lambda expression itself. With deducing this, you can do that. So to leverage this, the first parameter of your lambda expression should be something like this auto self. And then instead of using this inside your body of the lambda expression, you use self. If const eval. The syntax is straightforward. You just write if const eval A else B. So as you can see, there is no condition. The braces in this case are mandatory. And the effect basically is that if this statement is executed at compile time, then we will be executing A, otherwise we will be executing B. Now, you might be wondering, why do we need this? Because we already have the isConstant evaluated function. So what is wrong if we write it like this? If isConstant evaluated, then A, otherwise B. Basically nothing. Both ways are almost equivalent, except if you use a new feature, if const eval, it's part of the core language, so you do not need to include any header. Also, if const eval cannot be used wrongly, while isConstant evaluated can. So some people think that isConstant evaluated need to be used like I'm showing here with an if const expr, but this is entirely wrong, because this will, at compile time, because of the if const expr, it will at compile time evaluate isConstant evaluated, which obviously is always true at compile time, so this statement will always execute A and never B. And finally, within an if const eval block, you can call other immediate functions, const eval functions. I'll give an example of it. So here I have a function f, which is a const eval, so an immediate function. And an immediate function always needs to be executed at compile time. It can never be executed at runtime. Next, I have a function g, which is a const expr function. And const expr functions, they can be executed either at compile time or at runtime. But only in the case when it is executed at compile time can we call f. So that's why I'm using if const eval here. And only in the first block of my if const eval, I can call f. In my else block, I cannot call f. And finally, if I have another const eval or another immediate function like this one, h, obviously I can always just call other immediate functions without needing to do any execution context check. Multidimensional subscript operators. Up to now, if you have some data and you want to access it with multiple dimensions, you either use the function call syntax or you use multiple levels of square bracket operators. This is not so nice. So now in C++23, we have proper multidimensional subscript operator support, which uses a syntax that you would expect. And implementing these is actually very straightforward. So you just implement your operator square bracket, and instead of accepting one index, you accept as many indices as you need. So in this case, I have a square bracket operator that accepts 3 dimensions. Attributes on lambda expressions. So up to now, you could already specify attributes for lambda expressions, but only on the function object that is generated by the lambda expression. So in this example here, I'm specifying that this lambda expression or this function object that is generated by this lambda expression is deprecated. And you specify the attribute right behind the parentheses for your parameters for your lambda expression. C++23 also allows you to add attributes on the function call operator of the function object that is generated by the lambda expression, and they appear on a different position. So this one, the deprecated, is right behind the parentheses, so this means this is an attribute on the function object. And this one is right behind the capture block, so this is an attribute on the function call operator of the generated function object. So in this case here, I'm saying that if I execute this lambda expression, I'm not allowed to discard the return value. So I have to do something with it. We already have a couple of integer literal suffixes. We have U, L, and so on. C++23 add a couple more. We have now UZ and Z. UZ is an integer literal for size t, and Z is the corresponding signed integer type. Why would you use them? Here is a small use case. So I have a vector of data here, and I want to iterate over that data. I also want to cache the size of the data in this count variable, and I'm using auto here because I want it to be able to compile on 32-bit and 64-bit platforms. But as written here, this will not compile because I is deduced as an integer and count is deduced as a size t. So this will cause a compiler error. With the new literals, you can just specify that the I should be on a size t, and this will compile fine. I'm taking questions at the end of the, thank you. You can remember the slide number. Auto decay. Obviously, in C++, we could already copy objects. So one way to do it is you write auto C equals X. This will make a copy of X named C, but since it has a name, this is an L value. C++23 adds the option for you to make a copy that is a PR value or a pure R value, and the syntax is one of these auto X, so either you use parentheses or you use curly braces. Here is an, albeit rather artificial example, which otherwise doesn't fit on my slide, but I have a function process which accepts an R value. And then I have a second function, process all, which accepts a vector of integers or a vector of data. And inside the body of this process all, I iterate over all the elements of my vector. And for each element, I'm making a copy with this auto I syntax, and I'm passing that as an R value to my process function, which only accepts R values. There are a couple of new preprocessor directives, so the preprocessor is definitely not gone yet. So we already have ifdef and ifndef. New now is elifdef and elifndef, and also warning. So you can now cause the compiler to emit a warning with any custom string that you want. With C++23, it's also possible to mark certain parts of your code as being unreachable. For this, you need to include a utility header, and the function is called std_unreachable. If you do actually call this thing, you are explicitly invoking undefined behavior, but it is used to cause the compiler to optimize your code. I'll give an example. So I have a function here, do something, which accepts an integer. And as the name suggests, this integer can only have the values 0, 1, 2, or 3. And then inside my function, I'm having a switch statement that switches on that parameter. And I'm handling, as you can see, I'm handling all the cases. I'm handling 0, 1, 2, and 3. But obviously, because I'm passing an integer, the compiler has no idea that I'm handling all the cases. So what it needs to do, it will have to generate some code in the final assembly to verify that the number that I'm passing in is between 0 and 3 before it does actually jump to the right case statement. Now, if I just add a default handler there, a default case, and I call std_unreachable, then the compiler knows, okay, the default will never happen. So in this case, it can just omit the check for checking if the incoming parameter is 0, 1, 2, or 3, and so that's a couple of instructions less in the final assembly, so a little bit more performant. Assumptions. Before C++23, most compilers already had support for assumptions, but it was compiler dependent. So with MSVC and ICC, you can use __assume. With Clang, you can use built-in assume. GCC didn't have it, but you can emulate it with this syntax. Now in C++23, one example of why you would use this, I have a function here, divide by 32, which accepts an integer. And instead of checking that x is greater than or equal to 0, I'm just assuming that it is greater than or equal to 0. In C++23, there is a standard way to express assumptions, and that is using this syntax. So why would you use assumptions? Again, this allows the compiler to write more optimized code. About Unicode, so now you can use Unicode assigned names directly inside your string literals instead of code point values. So here I have an example. Before C++23, this code represents the UTF-32 character named Latin capital letter A with macro. So yeah, if you just read that in code, it's very hard to see what it is. Similarly, I can combine two Unicode code point values, but you have to specify the hexadecimal numbers. With C++23, you don't need to use the numbers anymore. You can actually use the official Unicode assigned name. So this is, I think, a bit more readable. And then this is an interesting one. So I have a piece of code here. I have a comment there that ends with a backslash line continuation character. And behind that backslash, there is an extra space. So if I compile this, what do you think would be the output of it? Just think for a second about it. Basically, it's undefined behavior. So if you run it with GCC and Clang, they will output 1. If you run it with MSVC, it will output 43. And both values are correct because the standard doesn't specify. But now in 23, the standard does specify it, and all the white space that is behind this line continuation character needs to be stripped. So the result of this piece of code should be 1. That's it for the core language features. So now let's have a look at the standard library features. And the first one, so C++20 introduced the stud format library to make formatting strings easier, and there have been a couple of improvements on that front. So the first thing is, besides stud format, we now also have stud print and stud print ln, and they make using stud format a little bit easier, because stud format is often used as follows. So I have some data. I have a name here, CppCon. And often how stud format is used is by piping it into stud cout. So you write stud cout, stud format, blah, blah, blah. And it's often that you're doing it like this. With C++23, you can write it more compact. You can write stud print and then your formatting string and the parameters. And you can also use print ln, which will automatically add a new line. So if you see here, that is lagging too much. So on the first one, stud print, you see there is a /n. On the print ln, there is no /n. Second improvement is that it's now very easy to format ranges. You can do that with stud format, with stud print, and stud print ln. And it's very straightforward. So here I have a vector of pairs, and I just print ln that vector. And then in the comment, you see what the formatted output will look like. So for the vectors, it will be between square brackets. If I have a set of pairs like here, then the output will be between curly braces. I can also output a map, and then the syntax is as follows with the colons in between the key and the value. C++23 also introduces two named modules. So first, you can do, from now on, you can do import std. And this will import everything from this std library. This includes all C++ headers, so that is std vector, map, set, sort, everything. but also everything from the C wrappers, stuff like std, fopen, and so on. And a second one named module is std_compat. It will import everything that std imports, but it also imports everything from the global namespace for the C functions. So if you do import std_compat, you can just write : fopen, otherwise you have to specify std fopen. C++23 adds 4 new containers to the standard. Well, actually, they are adapters. The first one here is flat map and flat multimap. They are defined in the flat map header. And as I mentioned, they are adapters on top of existing sequential containers. So you can use either a vector or a dec as the underlying container. And what a flat map provides is an associative interface, kind of the same as a std map. So it provides, or it supports unique keys, and it provides very fast retrieval of values based on a certain key. Just like std map, the keys are sorted based on a given comparison object. And as I mentioned, you can either use a vector or a dec as the underlying container. And a flat multimap is similar to a flat map, except that the keys don't need to be unique. And then the two others are flat set and flat multiset. They are defined in the flat set header, and very similar to the normal std set. So they just contain keys and they don't contain any values. How to use them? If you know how to use std map or std set, you know how to use these new ones. So I just define here a flat map with keys that are of type int and values that are of type std string. If you want to change the underlying container type, you have to specify this as 2 extra template type parameters. So in this case, I'm constructing a map where the keys are integers, where the values are strings. And I specify the third template type parameter is, or the fourth one is, the type of the container used for storing the keys, and the last one is the type of the container to store the values. MDSpan, it's a multidimensional extension of the existing std span, which was introduced in C++20. And yeah, to be as broad usable as possible, it supports different layout policies. And what is a layout policy? A layout policy is a function that converts a multidimensional index like ijk, which is a 3-dimensional index, into a 1-dimensional offset. And next to that, we have a sub MDSpan, which can provide you with a slice of an existing MDSpan. So let's look at an example. I have here some data that's coming from somewhere, but it's just a continuous block of memory. And then I can use MDSpan to interpret that block of memory. In this case, I'm interpreting it as data that represent 2 rows of 2 columns of integers. And once you have your MDSpan created, you can use the extend function to ask for the dimension of each, or for the size of each dimension. And you can use, inside the inner for loop, you see that you can use the new multi-dimensional subscript operator to actually access elements of your span. C++20 introduced coroutines, but up to now they were very complicated to write yourself. So I always recommended see if there is a third-party libraries that you can use for using coroutines, because implementing them is not straightforward. Now with C++23 we have one standard coroutine, and it's called a generator. Let's look on how we can use it. I have a coroutine here, getSequence generator, which accepts 2 parameters, a start value and a number of values, and it returns this new std generator coroutine. In the body of my coroutine, I'm just iterating from start value until start value plus number of values, and on each iteration, I'm co-yielding a value back to the caller. And then in my main function, I just call my getSequence generator, which returns me the the stud generator. I then iterate over the values of the generator, and I output each value to standard outputs. A small one, but maybe long overdue. Basic string and basic string view now finally contains a method contains, and it allows you, I have a haystack here, and I can search in my haystack for a C-child string, I can search for a character, or I can search for a string view. So it's finally no longer necessary to use find and then comparing the returned iterator with the end iterator of my string. And talking about strings, there is one other small change. In C++20, I could construct a string and initialize it with null PTR. This will compile fine, but this is undefined behavior at runtime. With a C++23 compiler, this should generate an error. So no more undefined behavior here. Finally, there is one new method called resize and override, and it has to do with performance. So it accepts two parameters, a count, which is a new size of a string, and an operation op, which will be called to fill in the new data in my string. So it will resize the string and set the content of my new string by calling that operation. So what is the effect? If count is less than the current size, we're just throwing away elements. If count is larger than the current size, then we append a number of default initialized elements, and then we call that operation that I mentioned. And the first parameter to my operation is a pointer to the beginning of my string, and the second parameter is the requested size of my string. But this is just a request. So what the operation can do, it can return me a value r, which can be less than count, and r represents the final size of my string. So then after this, we have to trim excess characters from the end of the string. So it sounds a bit complicated. Let's look at an example. I have a function here, generate pattern, which accepts a pattern and count, and it will just create one string with the given pattern repeated count times. How to implement it? Well, we can first create a string, which we will return at the end of the function. For performance reasons, we just pre-allocate enough memory in my string, and then we loop count times, and on each iteration, we append another pattern. What's the problem here? Well, with this iteration, we are writing count times, we are writing the null character, and also on each iteration, we are updating the size of my string, and we are checking if the string needs to be resized. Even though we did reserve enough space in the beginning, the checks are still happening. With resize and override, you call resize and override with the first parameter the size of your string, which in this case is just the size of my pattern multiplied by count, and the second argument is my lambda expression, and inside my lambda expression, I'm just filling in my string with the desired patterns repeated a number of times. And by doing it this way, you see there are no redundant null characters being written. The size of the string is not constantly updated either, and we don't need to check on each iteration if the string needs to be reallocated to provide more space. I do suggest, though, to only use this when performance is critical, because it's a bit less readable than the straightforward implementation. So when you're using stud optional in a chain of operations, then on each step in the chain of operation, you would have to check if the optional actually does contain a value or whether or not it's empty, because if it's empty, you should stop your chain of operations. So this leads to quite convoluted code. With monadic operations coming in C++23, you don't need to check anymore for optionals being empty. And there are three operations that you can do. The first one is transform f, which returns an optional containing the result of the function that I'm passing in. If there is a value inside my optional, if there is no value, then it returns an empty one. And then, also with a given function, it returns the result of invoking my given function. If my optional has a value, otherwise an empty optional. And or else just returns my optional if there is a value, and otherwise it returns the result of invoking f. It's a bit cryptic, so let's have a look at an example. I have a simple function here, parse, that accepts a string. And inside, I'm just trying to parse the string as a number, and if that fails, I'm returning an empty optional. Now in my main function, I'm just having a loop, and I get some numbers from standard input and try to parse each of these numbers. So I just call my function parse, which returns a stud optional. But remember that return stud optional can be empty. And then if it is successfully parsed, then I want to double the number. So I just write and then with my lambda expression to double the parsed number. And after that, I want to transform it into a string. So I use a transform monadic operation to return the string version of my value that was multiplied by 2. And if the parse failed because I input a string that is not a number, then I say or else, and I can return some no integer string. And you have some possible output here. If I type the number 12, I will get 24. If I type something that's not a number, I will get the no integer string. As you can see in this code, I'm not checking anywhere that my optional is empty. Everything is happening automatically because I'm using these monadic operations. The stacktrace library, it lives in the stacktrace header, and it allows you to get and iterate through all the frames of a stacktrace. It's rather easy to use. To create one, you just use stacktrace current, and if you just want to output to a stream, you just stream it to an output. And the latest version of Visual C++ does support this already, and this is one output from Visual C++. As I said, you can iterate over the different frames in your stack trace. Straightforward, I just create my stack trace, and then I have a range-based formula, which gives me each frame on each iteration. And then I can do something. I can ask a description. I can ask for a number of different things from that frame. And again, this is some output from Visual C++. C++20 introduced the ranges library, and in C++23 there are quite a lot new features coming to stud ranges and stud views. So first let's have a look at stud ranges. New starts with and ends with, and its use is trivial. So here I have two vectors with some data, and I can ask if v1 starts with v2, which is true in this case, or I can ask if v1 ends with v2, which in this case is false, so it prints a 0. Shift left and shift right, so you can shift the elements in a range left or right a number of places. So here I have a vector of strings, A, B, C, D, E. I can shift everything left by 2 positions, and I get C, D, E, and then the elements that are left over are set to the empty string in this case. I can shift everything right, and then I have an empty string, and then C, D, E, and an empty string. Before, it was already possible to convert a range to a container, but it was not straightforward. It required a couple of lines of code. Now in C++23, you can use ranges too. So here I'm using the IOTA view to construct a range of integers from 1 to 4. And then I'm transforming them, I'm doubling these, so the range contains the numbers 2, 4, 6, 8. You can easily double check that by printing them out to standard output, so here it will output 2, 4, 6, 8. And if you want to convert this range, it's rather straightforward. Now you can just do ranges 2, and then the type of vector the type of container that you want. In this case, I'm converting to a vector, and then your range. It's now also possible to find the last element in a range based on a number of criteria. So you can find the last element in a range that matches a certain value, or you can find the last element in the range that for which a given predicate returns true, or for which a given predicate returns false. What they return? They return you a subrange that starts at the element that was found in my range until the end of the range. If nothing is found, then it returns you last. You can check if a range contains a certain value or if it contains another range. So here I have two vectors again with integers, and I can check if v1 contains the value 22, which is true in this case, or I can check if v1 contains v2, which also is true in this case. Folding algorithms, so with C++23, you can fold the elements from a range either left or right. Let's look at how that looks like. So I have a vector of elements here, 11, 22, 33, 44, and I'm folding them left with stud plus as the operator. So what this does is basically it calculates 11 plus 22 plus 33 plus 44, which is 110. That's it for the ranges. The views library also contains quite a few new things. So now you can zip elements in a view or zip transform them. This is the kind of official description of these functions, but it's easier if we just look at an example. I have a couple of vectors here. For R1, I'm calling zip on V1 and V2, and what this does is it creates a new view with tuples, and each tuple consists of the first element of the first view and the first element of the second view, and so on. So if you do this on V1 and V2, you will get 1A and 2B. And then you see that V2 contains 3 elements, but V1 contains only 2, so then the C is dropped from the resulting view. And zip transform will call a certain operation on the elements of the different views. So in this case, I'm calling zip transform on V1 and V3, so 2 vectors with integers, and I'm using the stud multiplies operator. So what it does, it takes the first element of V1, multiplies it with the first element of V3, which results in 3, and then 2 times 4 gives me 8. And again, because V1 only contains 2 elements, the third element from V3 is lost. Adjacent and adjacent transform. So I have a vector of 4 integers, 1, 2, 3, 4, and if I call adjacent 2, it means that it will take 2 elements of my vector and put that in a tuple, and then it will slide along until it is at the end of my vector. So in this case, with input 1, 2, 3, 4, the resulting view will be 1, 2, 2, 3, and 3, 4. Also here, there is a transform version. So in this case, I'm doing adjacent transform with 2, and I'm using stud multiplies as the operator. So then it takes the first 2 elements of my vector, 1 and 2, and multiplies them, which results in 2. And then 2 multiplied by 3 is 6, and 3 multiplied by 4 is 12. Talking about adjacent, there is a template parameter there between the brackets, so you have to specify how many elements it has to take from your source view. But since often we are working with pairs, there are 2 helper types. We have pairwise and pairwise transform, which correspond to adjacent to and adjacent transform to. So here is another example where I have a vector of characters, and I'm looking at the V2 in a pairwise way, so I get AB and BC. And here I'm transforming the elements 3, 4, 5, and this time I'm using the plus operator, so I get 3 plus 4 is 7, and 4 plus 5 is 9. Slides. So remember that adjacent had a template parameter, so it's a compile time parameter. Slide is very similar to a JSON, but here the number is a runtime parameter. So other than that, the effect is the same. So if I have a vector of data and I call slide2, it's doing exactly the same as a JSON2. So in this case, I get the tuples 1, 2, 2, 3, and so on. And then chunk is a bit similar as adjacent and slide, but the elements of the resulting tuples are not overlapping. So here I have my input is 1, 2, 3, 4, 5, and if I do a chunk 2, I get tuples or pairs 1, 2, 4, and you see the last tuple is just containing one element because my input contains an odd number of elements. And chunk by is very similar to chunk, but it uses a predicate to group the elements. So here I have some data, 1, 2, 2, 3, and then 0, 4, 5, 2. And I'm using chunk by, and I specify that I want to use the predicate or the operator less equal. So as you can see in the output, the first tuple contains 1, 2, 2, and 3. And then we start a new tuple because the value of 0 is less than the value of 3. So then the second tuple is 0, 4, 5. And then we start another tuple because the value of 2 is less than 5. So then this is the final result. Join with, it allows you to join elements of a range with a certain separator. Here I have a vector of strings. It contains 3 strings in this case. And I can use join with to join these strings with a new line character, and then just output it. And then in comments, you see what the result would be if you output it to standard output. Stride, it's a view, well, it results in a view that provides an even or a strided subset of a given range. So let's look at an example. I have, my input is 1, 2, 3, 4, 5, and I call stride2. So then it takes every second element in my range. So in this case, it takes, the final view will be 1, and then it skips an element, so 3, and then it skips another element, so 5. Repeat, so you can either repeat a certain number or a certain element an X number of times, or you can repeat it infinitely. So the first one here, I'm repeating the value 2 3 times, or the second one is I'm repeating the value 2 an infinite number of times. Cartesian product, as the name suggests, it calculates the Cartesian product of a given number of ranges. So here I have a vector v, 0, 1, and 2, and I'm calculating the Cartesian product of v with itself and outputting the result. So in this case, the result is this sequence 0, 0, 0, 1, 0, 2, and so on. SR value. SR value will return you a view of some kind of underlying range, but where all the elements are now R values. So here is an example. I have a vector of strings called words, and I have an empty vector of strings called moved words. And what I want to do is I want to move all the words from my first range into the second range. So I can just use words and pipe it to SR value. So all the words are becoming, all the strings in words are becoming an R value, and then I can just use a back inserter to insert them in my other vector. All right, that was it for ranges and views. Next one is std expected. It lives in the expected header, and it's basically a class template with 2 template type parameters. The first one is t, which is the type of a value that you expect, and e is a type of the error that you want to return. And the guarantee here is that's never empty, so it either does contain a value of type t or it does contain an error of type t. And if you want to store it an expected value, that is straightforward. I'll show you on the next slide. If you want to store an error or a value of the error type, then you have to use stud unexpected. So here is an example. I have a stud expected where the expected type is an integer and the unexpected type is a string. So here A is initialized with the type, so I can just initialize it with 21, for example. If I want to initialize it with the error type, then I have to use stud unexpected, and then I can specify the string that I want to use. What can you do with a stud expected? You can ask if it has a value. So if there really is an instance of type t inside, then it will return true, otherwise false. I can actually ask the instance of type t, but you can only do that if there is really an instance of type t, otherwise it will throw this bad expected access exception. And finally, I can ask what is the error, and here also you can only call error if there is actually an error. Move only function. It's a bit an artificial example, but just to show what it is. I have a process function here that has one parameter, and the parameter is a function that doesn't accept any parameters and which returns an integer. And then inside, I'm doing something with that function. We can call it like this. So I can call process and pass it a lambda expression that just returns 21. That's no problem. I can try to call it like this, where I have a lambda expression with a capture block, and inside that capture block, I have a capture variable p, which I'm initializing with a unique pointer using makeUnique. This will not compile. So you will get an error like attempting to reference a deleted function, and the reason is that my stud function parameter to the process function will try to make a copy of the lambda expression that I'm passing in, which of course is not possible because this lambda expression contains a unique pointer. So in this case, you can easily fix this problem by using stud move only function instead of stud function. And now both just the simple lambda expression which returns a hard-coded 21 or the lambda expression which captures a unique pointer, both of them will now compile fine. SpanStream, it allows you to work with all style or C-style buffers. So there are two of them. You can have an iSpanStream or an oSpanStream. iSpanStream can be used to parse data in C-style buffers. So here I have a C-style data buffer with some integers in it, and then I can wrap that buffer inside an iSpanStream, and then I can use the normal extraction operators to parse that data. The other way around as well, so I can use an oSpanStream. So I have some data buffer here with 32 bytes. I can wrap it inside an oSpanStream, and then I can use the familiar C++ style of streaming data inside that C-style buffer. Byte swap, it's defined in the bit header, and it's a standard way to swap bytes. So this is a small utility function. It's easy to use. I have here an integer a. If I output this in hexadecimal notation, I get 1, 2, 3, 4, 5, 6, 7, 8. If I call byte swap on a, then you will see that the individual bytes are swapped. So I have now, the output of this will be 7, 8, 5, 6, 3, 4, and 1, 2. Two underlying, this is a very interesting one. It's defined in utility, and basically it converts the value of an enumerator to the underlying type. So before this was possible, you could use a static cast and then use the underlying type t type trait to convert it, but this is rather complicated. So let's have a look at an example. I have an enumeration here, color, and I'm defining a color R initialized with the color red enumerator. If I now want to actually get the value of that enumerator, in the past you do static cast underlying type t color R. This is quite cumbersome. Now you can just say to underlying, and it will just give you the underlying value of the enumerator. So I don't remember exactly which standard introduced, but we already had, before C++23, we already had heterogeneous lookup for associative containers. So that's both ordered and unordered associative containers. And what this means, it prevents creating temporary objects of the type of your key. For example, here I have a set which contains std strings. And then I'm trying to find the string hello, but I'm passing the string hello as a C-style string. So in the past, this would mean that a temporary std string is created that is initialized with the string hello, and only then is my find function executed. So thanks to heterogeneous lookups that were introduced previously, this code will not cause any temporary std strings to be generated. What C++23 adds is that this is now also the case for the erase and the extract methods. So if you have a std set containing strings, calling erase or extract with a C-style string will not cause the creation of temporary std string objects any longer. And then finally, so that's it for the standard library. Then finally, there is one feature that was removed from C++23, and that is support for garbage collection. So this was introduced in C++11, but I'm also not aware of any API or any library that's using this thing. And it seems it was decided to let's just remove it in C++23. So that's it. Right on time. So, any questions? Yeah, there is a microphone over here.
Thank you for the talk. Nice overview of everything. So on slide 20, you mentioned UZ. Do you need any header? Do you need to include a header to actually use the literal or not?
No.
No, so
it's part of the language.
Built in, and it will alias std size t, even though you might not include standard def, right?
Yes, this yeah.
Line 35, it was std println. I assume it's going to be the same as printing out a new line character, not flashing. Is that correct?
Yes.
Okay. Yeah. And slide 42, you show flat map, and you can basically specify two containers, one for the keys, one for the values. So as far as I understand, there's going to be two contiguous storages, one with all the keys, one with all the values.
Yeah.
And is there an API to iterate over all the values or all the keys independently? Do you know about that?
I think not. No, no, I think not.
Okay.
No.
Thank you.
I was quite excited for deducing bits. I think it's going to be very features to have the language. It's very close to something. Also, I'm quite keen on unifying functions from syntax. It feels as though deducing this is only a stone's throw away from having this in the language. This is perhaps a more opinion thing, but do you think we'll ever see that?
Not sure. I think there is another conference that you can ask. No, I have no idea. No, you're right. This can be indeed a stepping stone in that direction, but I have no idea how far they are with that. So I'm not part of the standards committee.
We have a question from online.
Okay.
On chunk by, maybe 75.
75. Yes.
What are the types of the resulting range value? They might have different size, so tuples might not be possible.
Sorry?
Oh, sorry. I was just reading. This is
I'm not quite following.
Oh, okay.
I
Sorry.
didn't quite understand the question. So.
I actually had the same question. What is the type of the element of the resulting range? Because the tuple size and types are a compile time thing, and here you're showing to be returning tuples of different size each time. So how is that typed?
How is it typed? It's all done at compile time. There are all different types, obviously. The first one is a tuple of 4 elements. The second one 3 elements. So
okay, I was under the impression the ranges are always a range of a certain type. So this is a range of different types?
I'm thinking it's a range of ranges.
A range of ranges, okay.
it's a range. Yeah, that could be, yes.
Okay, thank you.
Thank you.
Thanks for the talk. The one question I had is, why do we need a different type for the move-only function and not have something similar to a vector, for example, where you can put in, if I'm not mistaken, where you can put in a unique pointer and then you can only move the vector, and otherwise you can move and copy it?
Well, yes, you could. In this case, for example, you could, of course, well, not on the previous slide. So instead of just calling my process like this, I suppose you can just move that lambda expression inside your call to process. Pretty sure that will work as well, but yeah, the new syntax makes it a little bit easier, so you don't have to explicitly move your this lambda expression into process.
But here it's already an R value, right?
Yes, but yeah, it is an R value. Yeah, okay, yes, I see.
So,
Good question. Yeah, no idea why they decided to do it like that. But.
Oh, another question from online.
but why? What is the reason for that?
The external API for a function has to be copiable. Whatever you put in it gets erased. It has no idea whether it's copiable or not after you put it in. So it has to guarantee that whatever you put in the function is always copiable.
Okay.
Oh, question?
Okay.
The CppCtrace function does not work well with static binaries on Linux. It can only retrieve memory addresses and not function names. Do you know if standard stacktrace will work better?
It should. The standard says you should be able to get the names. So as you saw in the example I gave from Visual Studio, you clearly see all the names. At this moment, GCC and Clang don't support it yet. But once they support it, they need to be able to give you the name as well, yes.
So thanks again for the talk. Quick question on the MD span page.
On the
Multidimensional span.
okay, yeah.
Yeah.
Where was it? Slide
20 something, I think.
No, it was
Or 40 something, sorry.
here. Yes. Okay.
Yeah. Okay. So in the example page, I guess. Yeah. So the square bracket with a comma, is that the new syntax in C++73? And can this be used elsewhere?
This is indeed, you mean inside the body of the inner for loop?
Yeah, in
Yes.
the for loop.
Yeah, so that's indeed the multi-dimensional subscript operator that I mentioned before, yeah.
Okay, cool. Thank you.
So of course, yeah, it only works on C++23, but MD-span is C++23, so it's not a problem.
I understand you're not on the standard committee, but I was wondering if you have any insight as to why unreachable was like std unreachable function rather than an attribute, like assume is, because it feels like it should be an attribute.
That's a good question. I don't know. Maybe it was better an attribute, not sure, because now there is a possibility for you to call stud unreachable at a place where you shouldn't call it, and then you're actually invoking undefined behavior. So in my case, I added to the default case, which I'm sure will never be executed because the value that was coming in was just 0, 1, 2, or 3. And I know I'm not passing anything else. But I could just call stud unreachable anywhere. and then it's undefined behavior. And maybe with an attribute that would have been better. I'm not sure about the reason. But that's a good point, yeah.
Thank you.
So I got two questions. The first is about multidimensional subscript. I believe it's about slide 16 or something.
I think we have to stop. I just see the sign, it's over. But you can always find me in the hallway.
Okay.
All right, thank you.